Roman, I need to thank you. Because when a lot of people see this kind of like, I don't know how to count. I'm good at this one. Okay. How many Pennsylvania license plates are there? A lot, right?
Over 5.
Good plan, good plan. How many possible phone numbers are available in the US system? Unfortunately, no, because there are restrictions on what digits can be used where. Do you know of any phone numbers whose area code, the middle digits are 3? It really is done, because the coding system only allows for a 0, 1, or a 2 in the area code in the middle. What happens when I have these restrictions on the way I'm counting? Well, fortunately for us, Seth, your original idea, 10 to the power of digits, is really an application of this multiplication idea. The fundamental counting principle says if there are n1 ways to do thing 1, and 2 ways to do thing 2, all the way up to nk ways to do thing k. So I got to do all these different tasks, and I want to do all of them. That underlined phrase is going to give me some headaches, so I need to figure out what it means. Pennsylvania license plates, where I started this game, right? What's a Pennsylvania license plate look like? Not a custom one, a generic one. 3 letters and 4 numbers. There's a little keystone in the middle. So, if I don't care at all about what the license plate looks like, just have letters on the left and digits on the right, how many options are there for that first slot on the left? Just this slot would be 26, right? Doing them one task at a time. That would be 26 because those are all letters, right? And if the first letter doesn't affect the second letter, doesn't affect the third letter, then they're independent of one another, doesn't affect. That's my definition of if they are independent. In probability and statistics, there's a more precise definition of what it means to be independent, but for us just counting, that's sufficient. They don't affect each other. Then here, how many options are there here? Just for this spot. Because 0 counts, same thing here. So the answer is 26 to the third times 10 to the fourth. How many license plates possible? $75,760,000. That's enough license plates just in the state of Pennsylvania to put a license plate on every single human being's ass in the state of Pennsylvania, many times over. Unfortunately, not all license plates are actually possible. Right now, if you buy a car and you get a new license plate, your license plate will start MV. Although I was just looking at license plates that started MT. That means they skipped something. What did they skip?
Trucks and cars are.
No. Just automotive license plates.
You.
They skipped U and U. MT to MV. They skipped over the letter U, didn't they? Why? Because then they spell words. Your license plate is MUD 3736. They don't do that. They won't let license plates in the state of Pennsylvania spell words in that first set of 3 letters. So they'll be restrictive on what kind of randomly produced license plate letters they generate. Also, the Department of Transportation keeps a list of license plates that they will refuse to issue even if you ask for them as custom plates. My favorite one is B88BB8B. Because when that sucker goes by, you have no idea what it says. The cops can't track it. They did this in the state of Florida too. And again, the federal Department of Transportation maintains a list of license plates they will refuse to issue. One of my favorite license plates they refuse to issue is that one. Anybody want to know why that's not allowed to be issued as a license plate? "4Q. Now say it faster. The state of Florida got caught once because one of the license plates they issued looked like that, which in and of itself isn't a problem. But there's a keystone in the center of the Pennsylvania license plate. Anybody know what's in the center of a Florida plate?
An orange.
An orange. That made it out on the street, people. Not a good idea. So the Federal Department of Transportation keeps a list of license plates that they will and will not permit out there. But there are still a huge number of possibilities, even when I add restrictions. I asked about phone numbers. A phone number with an area code consists of 3 parts. The area code, the exchange, and the extension. When the Nationwide Telecom Act started in the 1950s, they made a rule the first digit could not be a 0 or a 1. In the area code, the second digit had to be a 0 or a 1. And then in the exchange, neither of these numbers could be 0s or 1s. How many phone numbers are possible? All you need to do is fill in each dash with the number of options available. 8 options, 2 options, 10 options, 8 options, 8 options, 10 options, and then 10 for each of these. And then I multiply. What do I get?
1,024,000,000.
Now, here's a problem. If you dial a campus phone number, what's it start with? That's our area code. What's the exchange? You pick up a phone to dial some office on campus. What's it start with? Turns out there are only two options. They either start 830 or 838. Why? Because Seton Hill was issued those exchanges. When you go to a cell phone company, you buy a cell phone, they used to issue you a number. Now you bring your number with you. But the first time you get a cell phone, they issue you a number. How do they have it issued? They bought an exchange worth. You buy numbers in lots of 10,000. My wife and I bought our cell phones together. We got sequential numbers because the company we bought them from had all 10,000 of those numbers available. And they gave us the next two in the list. That's not enough. So I believe it's 1993, 95, somewhere in the 90s, they revised this. And the revised telecom said, we're going to do away with this restriction. We're going to do away with the restriction on the middle of the exchange as well. With that change, how many numbers are available? Because all I do is I change this 2 to a 10, and this 2 to a 10. I get 2 more 10s. All I have is 2 8s, and everything else is a 10. That's not a factorial. Please note, that is all restricted to the United States of America. When you start dialing internationally, you have to have a country code in front of this. And then you have to do the Telecommunications Act for whatever country you're dealing with. So international calling takes a large change here. We've done this before. We just didn't think of it as counting options. Oh, and by the way, because of the way in which we count all of this, we keep changing the area code map in the state of Pennsylvania. 2017, they put a new area code over Harrisburg. In 2018, look at the Philadelphia area. There are 2 area codes there. In 2018, less than a year later, they added another area code. Because people were buying up exchanges. As we got more and more phone companies into the game, more and more people with more and more phone numbers. So, how do I figure out how many functions are possible? The rule for a function. Say again?
Same input, same output.
That's a specific rule for a kind of function. That's a one-to-one function. I didn't say anything about this being one-to-one. I didn't say anything about this being onto either. This could be any function, right? The only rule is for each input, you have to have an output. Just one, right? So, I could take a look at everything in A. Right? And then over here, I've got all the stuff in B. And I can say, I'm going to assign some element, BI, to the first thing. I'm going to assign some element to the second thing, right? I could assign the same output more than once if my function is not one-to-one. I could miss an output on the right-hand side, then my function wouldn't be onto. That's fine. But how many choices are there for A1? There's one that I choose, but how many choices are possible? I don't know how many things are on this side, but I can just take the cardinality B, right? And how many times am I going to make a choice? I'm going to make a choice for every element in A, right? So I'm going to take that many choices for A1 times that many choices for A2 times all the way up so that I've done this as many times as I have things in A. Which gives me the cardinality of B raised to the cardinality of A power. Remember when we talked about the power set and an element was either in or out and we did 2 to the cardinality? Same idea here. Only my choices aren't in or out, it's which choice is my landing zone. Questions? The base rule of counting. If I know all the different options that are available, I want to do all the things, I have to multiply. I don't want to do all the things. I just want to do something. Same setup. Suppose I want to do, and there are n1 ways to do thing 1 and 2 ways to do thing 2, all the way up to n k things to do thing k. But now, I don't want to do all the things. I just want to do one thing. How many ways? How many choices do I have? That tells me which thing I'm doing, but it doesn't tell me which way I'm going to do it. If I pick thing 2, there would be n 2 ways to do it, wouldn't there? Oh. And I could then pick any one of those, couldn't I? I want to know how many choices I have. hang on a second. Let me go back and think about that multiplication idea again for a minute. The multiplication idea, I want to do thing 1 and thing 2 and thing 3. I gotta go back to sets, chapter 2. Cartesian products. I made ordered pairs, right? And we used the word and we multiplied to figure out all the options that were available to us. What word would I ask you to use to decide between which thing you're going to do? You're going to do thing 1, thing 2. What word was in the middle? What did we use in logic, in sets, when we were doing ORs? That's our symbol, right? That V shape. But we were counting stuff. We were doing cardinality and counting the number of things in a set. Chapter 2, section 2 or 3, 1 or 2 there. Go look. You have your notes, you have your books. Go look. I used the word or. How did I then count things? The number of things in A or B. Wait a minute. In sets, we didn't use this shape. In sets, we used
Like this.
a union, a U. So I need you to find me the counting formula for a union. What did we do with those things? I came up with a number and a number. I didn't just lay 2 numbers down. What did I do with them? I added them. This is an or. Do thing 1 or thing 2 or thing 3. So pick from N1 things plus N2 things plus, aha. The number of options here is N1 plus N2 add all the way up to NK.
So for whenever you say you only want to do one thing, you're not saying that n equals 1.
No, I'm telling you to pick one of these things to do, right? I'm going to study. I have an exam in a couple of weeks. In each of my classes. Finals are only a month away, people. I got a final in each of these classes. I need to study 9 sections for one class. I need to study 8 sections for another class. I need to study 3 sections for a third class. I'm going to study one thing today. How many choices do I have? 9 plus 8 plus 3. I'll study one thing tomorrow. I'll study, and I'll just keep studying until I get to the exam. Now that does make an assumption. It makes the same assumption we made when we were multiplying. And that is that these are,
They're independent from each other, so if you choose one, you don't take it out of the set or anything like that.
well, once I've chosen it, it doesn't depend on anything else, right? It doesn't influence anything else. For example, it might be that it doesn't make sense to study the second section without already having studied the first. So maybe I have to do these in order. Maybe I don't. It depends on what the topics are and what the tasks are. But if these are set things, then these are, Selena, I'm going to put you on the spot here. That adding formula went with a picture. Picture of 2 circles next to each other in the Venn diagram. The name for those kinds of sets. Conjunction's that thing. 2 sets. in the Venn diagram, I drew the two circles, I drew them like this, rather than like that. So what was the descriptor we used, the adjective we used for these? Distinct is close, but not quite. But there are two of them. That would be when they overlap, they have no intersection, disjoint, close to distinct. So we're thinking of these options as disjoint sets of things to do. I promise, I'm not teaching you stuff that is in a vacuum. It relates to each other. So this is really a disjoint set idea. Questions? More complicated counting problems get built from these roots. I'm just going to go for the moment with a simple password system. It's not case sensitive. And it only uses the symbols above the number keys. You can't use any other symbols. So, I want a password that's 8 letters long. Well, 8 characters long. How many options do I have? Wait a minute, an 8-character password. Let me assume for the moment I had no restriction. If I had no restrictions, let me ignore this must contain at least one number line. How many options would there be here? Because there would be 36 options for each of these. That's a big number. I don't know what it is off the top of my head. But this will include passwords I'm not allowed to use. What should I do with those things when I count them?
Take them away after you're done. So count them in a different set.
The things I don't want to include, wait a minute, I used and, I used or, what am I using now? Using not. And when we counted complements, we subtracted. So I'm going to figure out how many things I'm not allowed to use and subtract them off. So, if it says I must contain at least one number, that means I cannot use what? All letters. So, how many passwords only contain letters?
You have 36, 37. Because you have to have at least one.
That's not what I've asked. Right now, I just want to know how many passwords use all letters.
26 to the 8.
Because now I'm only allowed A, B, C, D. Well, yaha, I can't use any of those extra symbols. So each of these spots would be 26, right? And those are the things I need to throw out. So my total number of choices is 36 to the 8th minus 26 to the 8th. Grab your calculators, give me a number.
$212,282,842,880.
What's 36 to the 7th?
$8 billion.
Oh, 78 billion. Stop right there. Look at how much smaller that number is. Why is that number so much smaller?
Because you subtracted 36 to the 7th, not.
I haven't subtracted, this is equal. This number is 36 to the 7th. Give me the rest of the set since you've got it in front of you. Oh, he got rid of it.
Okay, 78,364,164,096.
This is 2 trillion, this is 70 billion. That's 2 orders of magnitude larger. Why did that number come up so much smaller? All you've told me to do is take away 1 spot. But the problem is I don't know which spot. And I have to make sure that all of those 7 are not all letters. If this is a number, that's fine, but that would make this 10 options, right? I couldn't just take it away. And then what if I chose this one to be the number? What if I chose that one to be the number? Ooh, I got a lot more options that way, don't I? And that means I have to count a bunch because it can be here or here or here. I got to add up a bunch more stuff. And that's why this number is so much smaller, because you've only done 1 removal. I could do it that way, but I'm going to have to do a lot more work to do it. By the way, I picked an 8-character password. 9 or 10 or 11 or 12, right? I might have to do this. 36 to the 9th minus 26 to the 9th, and then 36 to the 10th minus 26 to the 10th, and then add up all those options. Your password for the Seton Hill my shoe stuff needs to be between 8 and 16 characters. I got a lot of options here. And passphrases can get longer and longer still. Say again? See, there you go. They're not short. Longer passwords are harder to crack. Case-sensitive passwords would make this option even bigger, right? You have to contain at least 1 lowercase and at least 1 uppercase letter. How do I figure all that out? It's this subtraction idea that gives me an interesting statement. We made the assumption that our categories were independent of one another, that they didn't affect each other. But what if my categories do overlap? This sounds like a really rigged question. It is. But the idea is not unique to this. This is still an or question, right? Can they start with 1 or end in 00? Well, if I'm gonna play the game we played before, I'll count how many things can start with 1, and I'll count how many things can end in 00, and I'll add them. That's my bit string that starts with 1. How many options are there for each blank? That's which blanks they are, but how many options are there for each blank? There are only 2 for each blank. 1, 2, 3, 4, 5, 6. There are 2 to the 7th options here. How many options are there? 2 in each blank makes 2 to the 6th option. There's just one problem. I counted a whole bunch of things twice, didn't I? Anything that starts with a 1 and ends in 00 is in both of these categories. If I counted it twice, I've overcounted. What do?
The one that says, not and,
I gotta do an and then I gotta knock that out. How many options there? This is 128, this is 64, this is 32. So I have 128 options plus the 64 options minus the stuff I double counted. Group 1, group 2, minus both. 128 minus plus 64 minus 32 is 160. Again, I've seen this before. When we were doing sets, Selena, now the Venn diagram has an overlap, right? Yeah. We counted the stuff in one, we counted the stuff in the other, and then we counted the intersection and removed it. We even wrote it as a rule. The cardinality of the union is the cardinality of the first one plus the cardinality of the second one minus the cardinality of the intersection. We call this the inclusion-exclusion principle. If you include something more than once, you need to exclude it once. A standard deck of cards. How many ways can you get a heart or an ace? Pick a card, any card. How many ways can you get a heart or an ace? Wait a minute. Unfortunately, no. And I don't want a probability. I want to know how many ways. Give me an integer. How many hearts are there? 13. How many aces are there? So 13 and 4 is 17 ways, right?
No, you have to take like ace of hearts.
Because it counted it twice. This sentence sounds really weird. I'm gonna stick with cards for a moment. I'm gonna go back to my nice shuffled standard deck of cards. And I'm gonna ask you to pick 2 cards, not 1, 2. How many different ways can you get 2 cards? No, standard deck of cards is just the 52. Say again?
That one.
But I'm getting both cards at the same time. So here,
2,652.
52 times 51. Yes. Okay. You got the Jack of Hearts and the 2 of Clubs. But they're in your hand. Do you know which one I gave you first? So if I gave you the 2 and then the Jack, if I gave you the Jack and then the 2, they'd be equivalent, wouldn't they? So do I really have this many options? If I only care about which 2 cards I end up with, not the order in which I got them, then I can divide by the number of equivalent ways. There are 2 distinct options here that are equivalent, aren't they? So the Jack of what, 2 of what, I've forgotten already. We'll make it up. The Jack of Diamonds and the 2 of Hearts. And the 2 of Hearts and the Jack of Diamonds as equivalent. And that means my collapsing idea actually divides this number in half. And there are really only 1326 distinct options if I consider them as equivalent to one another. You're all still looking at me kind of weird here. Let me give you another example. I am going to seat 4 people at a table. But it's not a straight table, it's a round table. Looks like I'm doing chemistry again. 2 seating charts are equivalent if the people have the same neighbors. First question. How many ways can you seat people? If you didn't care about being particular about who sat where, how many different ways could you put people in those chairs? Why?
Because there's 4 chairs and I'm assuming 4 people.
Well, if I'm going to sit 4 people at this table, then I have a problem. There aren't really 16 options. Because I'm going to put somebody here. How many options do I have? Then I'm going to put somebody here. How many options do I have? 4 times 3 times 2 times 1 is 24. But how many are equivalent? Let's consider one arrangement. I could rotate that, yes. There are 4 options if I rotate, but there are more. Well, maybe there are more, right? If I switched B and D, don't they still have the same neighbors? If I switch A and C, don't they still have the same neighbors? So if who's on your left and who's on your right matters, you're correct. If having the same neighbors doesn't care who's on which side, then there are more options, right? Well, that means either 4 options are the same or 6 options are the same. If we run with your idea, everybody has to be in the same relative position, then you tell me that all 4 of those options are the same. In which case I would say, oh, then there are really only 6 different seating charts. If neighbors could be left, right, or right, left, then I would divide by 6 instead of dividing by 4. I'd figure out how many equivalences there are. This idea of handedness matters. Here's the version with 3 people at 3 tables. Sorry, 3 people at 3 seats, right? Whether they're the same just by rotation or different by rotation. Another thing we can do to make our choices clearer, especially when things are not independent, is to draw out our options. Ian, you said 52 or 51, depending on whether I put the card back, right? So I can think of my choices as a sequence of decisions. Make them one after the other. I need to go to 2 stores and then home. 3 stores and then home this afternoon. So if I need to go to those 3 places, I leave here, I go to the first one. There are my choices. But now, because I've already been to store A, I shouldn't put another A after this, right? I'm not going to do 3 times 3 times 3. I'm going to change my number of choices at each step. And there are my 6 total options. A tree diagram like this is fairly helpful, but can get unruly fairly quickly. One of the problems in the older version of the textbook said, if we're going to have a World Series, how many different ways can the World Series end? How many different sequences of wins and losses are possible in the World Series? Because the person who wrote this problem liked New York, they had the Mets play the Yankees. There are a crap ton of options from somebody winning 4 in a row to they lose 1 and then win. Look at all the branches. I get 70 different choices. counting them to try and find some formula, I'd be here forever. Tree diagram, I just have to write them all out, make sure I'm missing. I like tree diagrams, I think they're fairly useful. We'll look at some more options on Monday. I will see you all then. If you came in late and I need your homework, please come give me your homework, and if I have stuff for you, come get it.